But in addition to whether these algorithms can run in parallel and how much communication that they take, we will also care about the basic running time of the algorithms. And one thing that may not be clear with Bellman-Ford yet is how many times we need to iterate. We know that eventually we get to a fixed point, but how many times will we need to iterate through all nodes before we get there? And it turns out that the worst case for Bellman-Ford is when you have this kind of linear graph where information from F needs to get to A and information from A needs to get to F. And each iteration is only going to be able to take one step, but it will take one step. So it'll take order number of nodes that we have in the worst case. With that thought in mind, let's consider the asymptotic complexity of our two algorithms. When we're using Dijkstra's algorithm for routing, then we will need to consider every node independently. That is, we draw a purple circle around each node one at a time. And starting from each of those nodes, we have to visit all the other nodes. That is, we have to turn every other node dark blue eventually. When we do turn a node dark blue, we have to look at each of its neighbors. And let's say that a node has at most m adjacent neighbors. In the worst case, m is the same as n. Every node is connected to every other node. But in a realistic network, m is often much less than n and something more like a constant. We check each of those adjacent nodes to see whether we update our estimate of the distance. And then we pick the smallest one to take the next step, the next one that will be turned dark blue. Technically, that takes log n time because we have to do some sort of search to find the smallest one. If you put all of this together, that means it's n times n minus 1, which we can just consider n squared, times m times log n. That gives us the complexity for Dijkstra's. For Bellman-Ford, we are going to do a number of iterations. On each iteration, we're going to consider each of the n nodes, and that m nodes will talk to its m neighbors, getting a table from each neighbor. When it gets a table, it has to consider every entry in that table, and that table has n entries because it's telling us the distance to all the other nodes. That was all just for one iteration, and then in the worst case, we have to iterate n times. So the asymptotic complexity of Bellman-Ford is m times n cubed. Offhand, it looks like Dijkstra is the clear winner here, and this is why it's the go-to algorithm for most purposes. But in the context of networking, despite n squared log n being much better than n cubed, we have to consider that Dijkstra's requires a kind of global communication. It needs to pick the best next step, and weights and nodes can't be changing in the background while we're working on one node to get its correct answer. Bellman-Ford, on the other hand, relies on local communication, so we can do each of the nodes in parallel, and each node only has to talk to its immediate neighbors, trading tables. Another subtlety is that while the overall global cost of Bellman-Ford is larger, we usually think of these n nodes in Bellman-Ford as being paid for by different people. And so from the perspective of an individual node, it's only doing one n of the cost and doesn't have to globally cooperate with everybody else, getting the full n cost. Also, when we're doing the local communication, and we're getting tables and we're doing another iteration, we really only needed to know the differences from the table of the last time that we received that table. We don't have to reconsider the parts of the table that were different. And so as the tables converge, then less has to be sent in those local communication and less has to be considered. So the actual cost here often ends up being much less than n, and similarly, this n was a worst case when we have things linearly arranged. Often it's much less than that.